they come, clickety-clack down the track. It's lots and lots of trains.
God dang it, where's my train? I'm gonna be late for the YSAT presentation.
Man, you know, if we were in Japan, this would have never happened.
Really? Why's that?
Because in Japan, they have trains that run in magnets, which makes them more efficient and fast.
Japan, huh? Hello, mate. My name is Angel Chavez, and today we will be investigating how the most efficient trains in the world operate on a daily basis. I'm sorry. Our independent variable will be the length of the Slinky, which we will manipulate throughout the experiment. Our dependent variable will be the strength of the magnetic field within the solenoid. Our hypothesis is that as we increase the length of the Slinky, the strength of the magnetic field inside the solenoid will decrease. This stems from the equation for finding the strength of a magnetic field within a solenoid. Our control group consisted of the measurement of the strength of the magnetic field at 60 centimeters. Our experimental groups consisted of every other trial after that, which included 20 centimeters, 30 centimeters, 40 centimeters, 50 centimeters, 70 centimeters, 80 centimeters, 90 centimeters, and 100 centimeters. Our extraneous variables included time, which were held at 10 seconds per trial, and we managed to keep all other magnetic substances away from the experiments in at least a 2 feet radius. In our experimental setup, we have two 6-volt heavy-duty batteries, gator clips, a metal Slinky, and a ruler which we use to measure the precise lengths of our Slinky. The first step in our experiment is to stretch out the Slinky to the precise length. In this trial, it is 60 centimeters. The next step in our experiment is to connect the ends of the Slinky to gator clips, which are connected to the batteries. At this point in the experiment, we have our LabQuest 2 program, which we nicknamed Cortana, connected to a magnetic field detector. We then insert the magnetic field detector for a period of 10 seconds into the Slinky. After we collected the data, we can look at the LabQuest 2 program and see the data collected. The time is measured from 0 seconds to 10 seconds, and we can see the data that it produces. Here, we have a graph and a table of our information. The table most obviously shows that as we increase the length of the solenoid, the strength of the magnetic field within the solenoid decreases. This shows an inverse relationship between the length of the solenoid and the strength of the magnetic field within the solenoid. Man, did I miss the train?
No, man, it's still not here.
Still not here? God dang it. Okay, well, I did an experiment with some friends, and I figured this out. I figured out that the trains in Japan work by running through a magnet called a solenoid. Now, this solenoid works by putting an electric current through a coil, right? And through an experiment with my friends, I used the length of the solenoid as the independent variable, which I manipulated, and then I used the strength of the magnetic field inside the solenoid as the dependent variable. And I figured out that there's an inverse relationship between the two. Now, I saw that as you increase the length of the solenoid, the strength inside the strength of the magnetic field inside the solenoid decreases. Isn't that amazing? What if we did that here in New York?
Well, did you expect that to happen?
Yes, I did. My hypothesis was found through the equation for finding the strength of a magnetic field in a solenoid. This equation shows that the strength of the magnetic field in the solenoid and the length of the solenoid are inversely related.
Well, do you think you could have improved the experiment?
Well, yeah, sure, I guess. Maybe if I had a little more time. I did this in the amount of time I could have spent waiting for a train, if it would arrive. And I guess if I had some better materials too, maybe a better Slinky, that could have improved it as well. Alright, here's the train. Finally! Alright. This isn't my train! Ah!